Hi everybody, welcome to Module 8. In Module 8 we're going to look at confidence intervals, and confidence intervals are the cornerstone of inferential statistics. And inferential statistics is a cornerstone of research. So there's a lot of value and application to the content that you're going to see the rest of the course. So our goal in this first video is to look at confidence intervals for population means and estimate a true population mean just by looking at a sample. So here's the example that we're going to use. An IQ test was given to a simple random sample of 75 college students. The sample mean was 105.2. Let's assume that the population standard deviation is 10. And let's estimate the population mean IQ for all college students. So at first glance, our best choice for estimating the true population mean would simply be the sample mean. And we call this a point estimate. But a point estimate might not be the best way to estimate the true population mean because, as we've recently seen, when you take a sample mean, it can come from anywhere in the distribution of sample means. And so 105.2 could be coming from the distribution of sample means, and it could be close to the population mean. It could be coming from the distribution of sample means out here. It could be coming from the distribution of sample means in this end, and we really don't know that, and we really never would. So we have to work a little bit more theoretically as we go through this. But this speaks to the fact that a point estimate is really not the best choice in estimating mu. So what we do instead is we quite literally try to give ourselves a margin of error. And so we're going to create an interval of values, and we're going to think about the possibility that the true population mean might be inside that interval of values. And so when you give yourself a margin of error and you give yourself an interval, then you're much more likely to cover that population mean than simply using a single point. And so that's the idea behind a confidence interval. It's to take a point estimate and then add and subtract a margin of error on each side of it. And so even though we don't know where 105.2 is in this distribution of sample means, if for some reason it was, let's say, right here, and I'm just completely pretending at this point, but if it was right there, then the point estimate would not have been a great estimate of my true population mean. But had it been right here and I created a margin of error on both sides of that point estimate, you could see that I would have created an interval going from this value to this value, and even though it's a fairly wide interval, it looks like that interval would have included the true population mean. And so we're going to talk a little bit about how do we determine the length of that margin of error, and a lot of it actually goes back to what you've seen before with the empirical rule. So let me remind you of the empirical rule, and that rule was also known as the 68, 95, 99.7 rule, and it said that when you have an approximately normal distribution, which again we know that our x bar distribution is approximately normal because we satisfied the central limit theorem. We know that 68% of our data in an approximately normal distribution is within 1 standard deviation of the mean, 95% within 2, and almost all of your data is going to be within 3. And I'm going to focus on this number in particular. And I'm also going to be a little bit more detailed than what I just was. So to be perfectly accurate, 95% of your data is not within 2 standard deviations of the mean. 95% of your data in a normal distribution is actually within 1.96 standard deviations of the mean. So if this distance right here is 1.96 standard deviations, and then I go onto this side also, and that's 1.96 standard deviations, then 95% of my data, or 95% of sample mean IQs would be in this range. So that's good to know because that tells us that there's a pretty good chance that our sample mean that we have in this particular problem is within a couple of standard deviations of the mean. And again, we don't know if that sample mean of 105.2 is here, or if that sample mean of 105.2 is here, or if it's here, or if it's on the left side. We have no idea. But we do know that there's a 95% chance that it's within 2 standard deviations of the mean. Now I can take that statement that each of these sample means that you see here is within 1.96 standard deviations of the mean, and I can turn that around in a way that's really going to help us out. So saying that each of these sample means is within 1.96 standard deviations of mu is identical to saying that mu is within 1.96 standard deviations of these sample means. And so we can see that mu is going to be within 1.96 standard deviations of the sample means 95% of the time. So let me write that down. I'm going to say mu is within 1.96 standard deviations of the sample means 95% of the time. And this is going to be really helpful for estimating mu because it's giving us some language that we can convert to math symbols, and it's going to, those math symbols are going to lead us to the specific interval that we can use that we're going to call our confidence interval. And so how do we take this and put it into math symbols? Well, to say that mu is within 1.96 standard deviations of the sample mean, we start with the sample mean, which is x bar, and we add and subtract 1.96 standard deviations in this distribution from it. And so the standard deviation in the distribution of sample means is sigma divided by square root of n. And so what we're saying is mu, what we're trying to estimate, is somewhere in this interval 95% of the time. So that means for 95% of sample means, this interval that you see right here, this x bar plus or minus 1.96 times sigma over root of n, for 95% of sample means, or 95% of sample mean IQs, this interval will contain mu. We call this a 95% confidence interval. But you should know that for one single specific mean, we don't know if our confidence interval, if this range is going to contain mu or not. Based upon the theory though, we would be 95% confident that it does. So that has implications for our example when we're thinking about the mean IQ. So the mean IQ, just following this formula now, would have an opportunity of being inside the following interval, 105.2 plus or minus 1.96 times 10 divided by the square root of 75. Remember, we assumed the population standard deviation to be 10 and the sample size was 75. So again, for this specific sample mean, we don't know that this interval that we're going to create, and I'm going to punch this into the calculator in a second, we'll look at that interval. We don't know that mu, the mean IQ, is in there. And so let's punch it into the calculator, get the interval, and then I'll talk a little bit more about that. So I'm going to do 105.2 plus 1.96 times 10 divided by the square root of 75. And that gives me, for an upper bound, 107.46. And then if we get the lower bound of this interval, we would say 105.2 minus 1.96 times 10 divided by the square root of 75. And we get 102.94. So what is appropriate to say here is that we are 95% confident that the true mean IQ is in this interval. All right, I'm going to say that again. We are 95% confident that the true mean IQ is inside this interval. Once again, we do not know if the true mean IQ is inside this interval because we don't know where our original sample mean is in this distribution of sample means. But 95% of the time when a confidence interval is created beginning with the sample mean, we know that that confidence interval is going to cover the true population mean. And so with 95% confidence, the true mean IQ of all college students is in this interval. So you should also know that it's not technically correct to say that there's a 95% probability that the mean IQ is in that interval. And so there's a big difference between saying 95% confidence and 95% probability, because mu is either in the interval or not, and we don't know that. So it's correct to say that the method for constructing a 95% confidence interval has a probability of 95% of covering the mean. So this idea of a 95% confidence interval can be nicely seen in the next video that I'm going to walk you through. It's a simulation, and you can look at a sampling process where you get a sample mean, you create a confidence interval, and then you get to do that sampling process and confidence interval creation process over and over and over again, and you'll see that some of your confidence intervals won't include your population mean and some of them will. But again, the proper language is when you create a 95% confidence interval, we say that we are 95% confident that that true population mean is inside that interval. And then that allows us to make some reasonable conclusions also. Like you could say it's reasonable to conclude that the population mean is between 103 and 107, statements like that. So take a look at the next simulation video, and then we'll get into exactly how you're going to be doing this. You're not going to have to worry about this theory so much, but I wanted to give you a little bit of background because we're going to be talking about confidence intervals so much. And you're going to be doing this a lot in your calculator, and you'll see that in the coming videos also.